Okay, let's move on to chapter 2. So in chapter 2, we will discuss Maxwell equation, in particular the Maxwell equation in integral form. And in chapter 3, we will discuss Maxwell equation in differential form. So they are both Maxwell equation and they are talking about the same physical phenomenon. However, the difference in integral form and differential form can provide you different aspects to look at electromagnetic wave phenomena. It's easier to understand the interaction of electrical field and source in terms of integral form. So therefore, we will learn integral form Maxwell equation first. However, before we proceed for the introduction of Maxwell equation, we have to learn a few mathematical tools in section 2.1 and 2.2. They are the so-called differential. Okay. All right. Okay. So in in section 2.1, we will talk about line integral, and 2.2 for surface integral. Then we will go into Maxwell equation. For your reference, we will have our first midterm next Thursday, and we shall cover up to section 2.2. Okay, section 2.2 for the first midterm. All right, so here is our first example. Suppose we have a charge placed on the background of electric field. So figure 2.1a shows the black solid line indicates the presence of electrical field. And here is a path from point A to B. The path C, if the charge is moved along path C from point A to point B under the background of electrical field, what happened to this charge? Well, there will be some work act on the charge. And how do you calculate the amount of work done in this moving test charge? So the purpose of the line integral operation is to evaluate the amount of work done on this test charge by moving it from point A to point B. So as you know, the electrical force is acting on a test charge along the direction of electrical field. So as long as the charge is moving in a direction that has projection on the direction of the electrical field, it will experience some work. On the other hand, if the charge is moved perpendicular to the direction of electrical field, it will experience no work. It will experience no electrical force. Okay? 所以你要对电荷做功，你必须要让这个电荷沿着电场的方向，或者是说它的方向有一部分的投影量是在电场方向上，你才能够对它做功，你才能够累积功。只要你的移动方向是跟电场方向正交的话，那就不会受力，也不会做功。Okay? And in this example, as we see, the curve is not a straight line, and as also the electrical field is not consistent or is not continuous, it's not a straight line as you can see here. It has some curvature. So to calculate the amount of work accurately, you need to do this calculation in short lengths. You need to divide the curve C from A to two small pieces and calculate the force exerted on this charge individually. And then you add up all the work acts on the charge to get the total work, experienced by this test charge. So similar is a strategy of divide and conquer. Okay, so if the length is short enough, if you divide this curve into many small short pieces, then you can assume that the section can be approximated as a straight line, and the electrical field within this region, within this short length, can be assumed to be homogeneous, can be assumed uniform, and well, it helps you to carry out the integration, carry out the calculation. So for very short lengths, the line can be regarded as uniform direction. And the path, that is delta L1, delta L2 in different locations, can be assumed to be straight lines. And the work, the field, not the field. The force experienced by the test charge is what? Is the projection of the field, say E1, on delta L1. So you need to times E1 with cosine alpha j, where alpha 1 is the angle between delta the L1 and E1. Okay, so E1 cosine alpha 1 give you the effective electrical field acting along the integration line. Okay, and the integration line, the L1 is referred to as the differential length. All right, then equation 2.1 give you the expression for the work accumulated by the charge Q on the small pieces of distance, the L, due to the presence of EJ, due to the presence of electrical field. So it simply is the equation of W equals to F times X. F is the force, X is the distance. The force times distance provide you the work, amount of work. And for a short distance dl, the work can be expressed as QE cosine alpha dl. Okay, so the next thing is add up all the work acts on the charge in individual short pieces. Okay, so we can be written as a summation for different positions, right? And according to the equation, we should know that the amount of work act on the charge is related to the path, the direction and the length of the path, right? So, however, later on we will introduce the idea of the so-called conservative force and non-conservative force， 保守场跟非保守场，那保守场的一个特例就是说它的功跟路径无关。那最简单的例子就是重力场，所以你 爬到3楼跟坐电梯到3楼，你所增加的位能是一样的啊，只是你消耗的是电能，还是你消耗的是你今天早上吃的早餐会不太一样OK。那对于电磁场来讲，静电场是 conservative field 静电场是保守场，但是电磁场不是电磁场不是所以对于静电场来讲，你的做功大小跟路径无关，但是对于动态的时变电磁场来讲，你的做功大小跟路径是有关的所以我这边的 footnote 是一个所谓的向量做功大小跟路径有关，但这其实还是跟你的场的性质是有点关系的是有关系的Alright, so WAB is the total amount of work done on this charge Q by moving it from point A to point B with the presence of background electrical field E. Okay, so here's one example. So I guess you probably can carry out this calculation by yourself, but let's look at this example really fast, really quick. So say we have, we want to move this charge from which has the amount of 3 microcoulomb. So it's a small charge, 3 times 10 to the minus 6. And the position is moving from A to B, which is 0, 0, 0, and 1, 1, 0. And it's moving along a parabolic path, that is, which can be defined as y equals to x to the square. So this is not a straight line. This is referred to as the parabolic line. 抛物线 y equals to x to the square. And well, there are many different ways to segment or to separate this parabolic line into small pieces. But in this example, the author divided it according to the position, x-coordinate position. So according to the x-coordinate, which is 0, 0.1, 0.2, 0.3, 0.4, and you use the y equals to x to the square equation to give you the y position. This one is 0.01. 0.04, 0.09, etc. Okay, so you define the observation point. So this is the x-coordinate, this is the y-coordinate. So in every section, the DL is approximated as a straight line like this arrowhead. In fact, this is part of the parabolic line, so this is not a straight line. But, well, in this short distance, it can be approximated as a straight line. Okay, so that is the general assumption for modern engineering. Okay, so we use the strategy divide and conquer so that you can simplify the calculation. Okay, you can simplify the calculation by divide the region of interest into very short pieces so that you can simplify the calculation. So it can be approximated as a straight line, and because it's a straight line and the electrical field, well, where is my definition of electrical field? Let me move back a little bit. The definition of electrical field is defined in terms of the y-coordinate. Okay, so E field is pointing in the y direction, and the amount, the magnitude of the E field is proportional to y-coordinate. Okay, so as the y-coordinate gets large, the electrical field intensity grows as well. So this electrical field is not homogeneous, and it's not very linearly according to the y position. It's kind of, it's very linearly according to the y position. Okay. All right. Anyway, so you have the expression for the y field. You have defined the geometry for your line integral. So you can use this relationship to write up the equation for the calculation of work made from point A to point B as the summation of individual differential length, as the scalar product of individual differential lengths and the E field in that neighborhood. All right, so you substitute the representation for delta L, dl, and Ej, and substitute them into this equation. So you can calculate the total work done for this problem as 1.3 microjoule. Okay, 1.3005, okay, to be exact, microjoule. And of course, this calculation can be carried out using line integral directly. But why do we trouble to introduce the idea of the so-called divide and conquer strategy? Why don't we just use calculus to solve this problem? Because we are engineers, we are not mathematicians, okay? So to handle general problem, engineer can devise a more general approach to deal with the problem. Of course, a mathematician might criticize your approach that, well, your solution is not exact, it's not that accurate. But for an engineer, I can say that under the assistance of my computer, I can exert my power of computation. So I can divide the problem into even finer grid. So as the division is, as long as you have, if you add up your division, that is, the mesh or the cells become smaller and smaller, the accuracy can be improved, and eventually the solution will approximate the exact solution done by calculus. So let's try solve this problem using calculus. So the expression is equation 2.4. So you can, well, this is a relatively simple problem in terms of calculus. So you do the differentiation for this equation. So that is first order differentiation. So originally the equation is 1 equals to x to the square, and it becomes dy equals to 2 times x times dx. And this equation has no relevance in terms of z. And you write up the general expression for differential length as we learned from chapter 1, like this. And you can replace dy and dz in terms of dx. So here you have dx ax plus 2 times x times dx ay. And then because you convert all the differential part into dx, then you can carry out the integration in terms of dx. So the next step is carry out the integration in terms of dx, because here you have a scalar product. So originally electrical field is a vector dl, the differential length is a vector as well, but because of the presence of a scalar product, they become a scalar. So the integration can be carried out easily. And as you can see here, the solution is 1.5 microjoule. So the mathematician will laugh at you, say, wow, your solution is 1.3 and the actual solution is 1.5. You are off by 10%, okay? Well, so even, 10% error is a little bit large, okay. However, if you divide the separation in not 10 pieces, but 100 pieces, I bet the error can be reduced to less than 1% or even smaller. Okay, so this is the power of divide and conquer, I guess. And here is another view to look at this integral problem. And this part is to carry out the integration in terms of y. Because here we have this relationship that dy equals 2 times x dx. Okay, so you convert dy into dx. Nevertheless, you can do this in a reverse way. You can convert dx as dy. Okay, so here you have the scalar product as y dy. Well, because electrical field is defined is actually determined in terms of y. Okay, so if you carry out this integration, it seems a little bit easier, but the solution is 1.5 microjoule as well. Okay, so you can do the integration, carry out the integration using dx, using x or y as you wish. Right? Okay, so the last concept I would discuss today is the concept of potential. So, as you can see here, the amount of work can be regarded as Q times this integral. So, Q is the amount of charge. So once you have an electrical charge placed in the background, you will experience the force, and if the charge is moved, you will experience the work done on this charge. So what is the thing except the charge Q? What is the physical interpretation of this integration? Well, this is not an actual physical parameter. This, however, the definition of voltage, VAB, is very helpful in treating this engineering problem. Okay? So we define this physical quantity, which is an imaginary one, as voltage, which in electromagnetics is referred to as electrical potential, 电位能。电压，所以这边我们就跟你讲了，电压是一个我们人为创造出来的物理量，它并不是真实的物理量，它事实上是电场乘上距离之后的结果。电压是电场乘上距离之后的结果，电场是真的，电压是虚构的，但它很好用，所以我们后来都用电压。OK？ So voltage, which is referred to as electrical potential in electromagnetics, is actually the product, the scalar product of electrical field and distance. So a more general way to express the voltage is equation 2.5. Now you carry out, so therefore you can the potential can be defined can be found for any arbitrary path using the expression of an integral. Okay. Then so I will leave up the discussion about closed loop growing or something like that in Thursday. Okay.